We are going to take a messy, unstructured pile of raw text files and turn them into a precise, continuously monitored conversational agent. Over the next 6 minutes, we will embed your custom data, wire it to an open-source model, deploy it to a cloud server, and set up live hallucination tracking. To build this, you need 4 things: a Python environment, a vector database to store our data, an open-source language model to process it, and a cloud account for hosting. Building a reliable AI application requires shifting your focus away from simply typing clever prompts into a web interface. You have to build a resilient, observable software architecture. This diagram outlines the Retrieval Augmented Generation, or RAG, architecture. It shows moving raw text into a system for immediate retrieval. First, we split documents into chunks, then run them through an encoder to create vector embeddings, mathematical representations of the text's meaning. These embeddings are ingested into a dedicated vector database. This database stores the mathematical relationships, allowing the system to find conceptually similar text instantly. We know this stage is successful when we can execute a semantic search query, and the database returns the exact document chunk that answers our query. This searchable database acts as a strict boundary. It grounds the model in your specific documents, preventing it from inventing answers based solely on the broad data it was originally trained on. Now we need an LLM framework. This is the code layer that connects your user's input, the vector database, and the language model into a single workflow. A common mistake is hard-coding context directly into static prompts. That approach breaks as soon as your data updates or your user asks a new question. As we see in this diagram, we use augmentation instead. The augmentation step automatically intercepts the user query, retrieves the relevant documents from the database, and appends them to the prompt before the language model ever sees it. To build this chain, you assemble 3 core modules: a prompt template to format text, a model to generate the response, and a chain to link them. Modern frameworks make this highly efficient. You can assemble a fully functional RAG application in roughly 18 lines of Python code. Dynamically chaining these components together is the exact mechanism that turns a static text generator into an active, context-aware agent. When we move to deployment, we hit a hardware wall, out of memory, or OOM errors. OOM happens when a model's parameters exceed available memory, leading to astronomical hosting costs. The technical solution is int4 wait-only quantization. Quantization is a technique that compresses a model by converting its parameters from high-precision floating-point numbers into 4-bit integers. By shrinking the data types, we drastically reduce the model's footprint in memory. At the same time, we preserve high accuracy, keeping the output quality within a 1% margin of the original uncompressed model. This chart compares the generation latency of a standard 16-bit model against an INT4 quantized model. The INT4 model easily hits the 20 to 80 millisecond target, which is significantly faster than the average human reading speed of 200 milliseconds per token. With the model optimized, we send a test ping to our newly live inference endpoint to verify the connection. Our metric for a successful deployment is receiving a grounded, coherent text response back from the server in under 1 second. Solving the memory bottleneck through quantization is the dividing line. It turns an expensive local experiment into a scalable, production-ready cloud application. This diagram maps out the machine learning lifecycle. Once the model is live, we enter the continuous monitoring phase, also known as LLM ops, the operational practices used to manage and track large language models in production. To track behavior at scale, we deploy machine learning judges. These are lightweight evaluator models programmed specifically to automatically score the main application's outputs. First, the judges track context relevance. This metric ensures that the retrieval process is actually fetching accurate and useful data from our vector database. Next, they track answer faithfulness and answer relevance. If the generated answer ignores the retrieved context or fails to address the user's prompt, the system instantly flags it to intercept ungrounded hallucinations or toxic responses. Without automated monitoring, an LLM in production is an unpredictable liability. With active scoring, it becomes a measurable, safe, and governable asset. We successfully routed a query to a vector database, retrieved custom context, generated a fast INT4 response, and scored the output with an automated judge. You now have the core operational pillars in place: version data, RAG-grounded responses, cost-optimized deployment, and monitored safety metrics. Eventually, you will encounter use cases where your domain vocabulary is so highly specific that RAG alone cannot provide enough context for the model to understand the nuances. When that happens, you need to adjust the model's internal weights. In the next video, we will explore Q-LoRa fine-tuning, a highly efficient method for training custom behaviors, so you can push your foundation model even further.